Welcome to our channel Learning Math. In this video, we're going to learn about transformations of planes. What's the meaning of transformation? What mappings can be applied in transformation of planes? Now let's start together. As you see here, we have a plane P that contains several points. We have the points A, B, C, and D. This plane, as you see, is translated. It undergoes a translation. If you note something, all the points of the plane are translated by the same vector. Here, the main vector of this translation is the vector BA. If you note, the point C is translated towards the point F by the vector CF, which is equal to the vector BA. Also, the point E is translated towards the point G by the translation vector EG, which is equal to the vector BA. The same here for the point D, which is translated towards the point H under the translation of the vector DH, which is equal to the vector BA. Well, what is this translation? Translation is a mapping that is applied to all the points of this plane. We say here we have a rigid translation since the whole plane moved from its place. Note something. We have the translation is under a translation vector V, which is different from 0. Here it's the vector VA. If we say it's 0, we should say that the plane remains in its place. There will be no translation if the translation vector is 0. So it should be completely different from 0. Well, let's learn more about this translation. If you note something, here the point C is translated towards the point F. We can say that the translation vector of C gives us the image F. So the image of C under the translation by translation vector V is F. Also, the image of E under this translation is the point G. So we can say that TV of E equals G. The same here, the image of D gave us the point H. So we can say that TV of D equals H. What about the inverse of this translation? If we talk about the inverse of this translation, the inverse of any function, we think what point gave us the image. For example, what point gave us the image F? Isn't it C? C is translated to give us F. So the inverse translation of F is the point C. We can say that T minus 1 of F under the vector V is the point C. Here also, what point gave us G under this translation? Isn't it the point E? So we can say that T minus 1 of G is E, sure, under the translation by the vector V. The same here, what point gave us the image H? Isn't it D? So we can say that T minus 1 of H equals D. Note something more. The more this vector of translation approaches 0, the more we can say there is no translation. Here the plane remained the same. Well, what are the transformation mappings that can be applied to planes? First of all, we should know the identity mapping. What's the meaning of identity mapping? If we have, for example, a point M, under the identity mapping, the image of M is a point M prime which is coincident to M. It's the same point itself. Here we talk about what we call the identity mapping ID. Another point N, for example, the identity mapping of N is N itself. It's an image N prime which is coincident to N, the same point. So same image. Here we talk about identity mapping. We can say that ID of M equals M prime and ID of N equals N prime. M prime and N prime are the images of M and N under this mapping. Well, sure, there's something which is very important. Since the location of M and N didn't vary under their identity mappings, we can say that M and N are said to be invariant points since their location remained fixed. The location of the image and the main point is the same. Well, what about symmetry? Symmetry is also a very important mapping that can be applied in transformation for planes. First, let's learn together what's the central symmetry SI. We call it Si the symmetry relative to a point I, which is said to be the center of this symmetry. If we have a point A, for example, and we want to find the image of A or symmetry of A with respect to I, sure, we join AI and produce it by the same length to give us the image A prime of A. Well, here we can say that Si of A, the image of A, is A prime. Another example, if we have a point B, its image under this symmetry is B prime. So the symmetry of B with respect to I is B prime. So here we can say that Si of A, the image of A under this symmetry Si, gave us the point A prime. So Si of A equals A prime. The same here. Si of B, the symmetry of B with respect to I is B prime. So B prime is the image of B under this symmetry. Something else which is very important. If we want to find the symmetry of I with respect to I, isn't it the point I itself? So Si of I equals I, in this case, I is said to be an invariant point. Its image is the point I itself. Well, what about the inverse of this symmetry? If we think about the inverse symmetrical function for A prime, what point gave us A prime as image under this symmetry? Isn't it A? So as minus 1i of A prime equals A. What about B prime? What point gave us the image B prime under this symmetry? Isn't it B? So we can say that as minus 1 of B prime is B. As minus 1i of B prime equals B. What about I? Since it's invariant, we can say that as minus 1 of I is I itself. Well, we have learned about the central symmetry. What about the reflection with respect to a straight line D? We call it SD, symmetry with respect to a straight line D. As you see here, we have a line D and a straight line D prime that is perpendicular to D. Here we will talk about the symmetry for points on a straight line which is perpendicular to the other one. If we take a point M on D prime, note that when we talk about the symmetry with respect to D, we should draw the perpendicular, which is already drawn since the two lines are perpendicular, and produce it by the same length. So here M prime is the image of M under this symmetry. Well, if you know something, M prime is located on D prime, since D prime is perpendicular to D. Another example, if we have a point N, its perpendicular is D prime itself, since the two lines are perpendicular. If we produce it by the same length, we get here N prime, which is also located on D prime. Well, so here we can say that under this under this symmetry, D prime as a whole straight line is said to be an invariant straight line. The image of D prime is D prime itself. Something else which is also important, if we talk about points which are located on D, if I want to find the symmetry of A with respect to D, but A is located on D, so the symmetry of A will be A itself. Also, for any point on D, the image of this point is the point itself. The points that are located on the straight line D are said to be invariant points under the mapping, symmetrical function as D. Well, let's learn here something which is very important. If we have a plane P that contains several points, as you see here, we have points A, B, C, and D on this plane. If I want to find the symmetry for each point with respect to the point D, for example, the symmetry of A prime with respect to D, is the point A prime. A prime, if you note, is located in the plane itself. Why? Since A and D are both located on the plane P, then the image of A under the symmetrical function with respect to D will be A prime located on the same plane. Another example, if we draw the symmetric of B with respect to D, B and D are located on the plane P, then the symmetric of B with respect to D will be also located on the plane P. The same for the point C. So also the image of C C prime is also located on the plane P. Well, what happens if we join the points A prime, the images A prime, B prime and C prime? If you note something, the plane containing these 3 points is coplanar to P. It's the same plane. Why? Since all points that are undergoing symmetry, in addition to the center of this symmetry, are located in the given plane. So here we can say that the plane P is invariant under this function. Something else, as you see here, we have a plane that contains several points A, B, and C. If we want to find the symmetry for these points relative to the straight line D, which is here, as you see, this line is the intersection of the plane P with the plane that is containing the axis x prime OX and y prime OY. If we draw the symmetric of A with respect to the straight line D, or with respect to the plane P, the plane containing x prime OX and y prime OY. As you see, the symmetry of A here is A prime. What about the symmetry of C prime? Also here the symmetry of B is B prime with respect to this plane. And the symmetric of C is C prime itself on the plane. Here the image of A is A prime. The image of B is B prime. While the image of C, which is located on the intersection of P and X prime OX, Y prime OY, the plane containing them, is the image C prime, which is also located on the line of intersection. Well, here if we see, this is the plane containing the images, which is said to be the image of the plane P under this symmetry. This is more obvious figure. So here, if you note that the straight line, the line of intersection of the planes P and the plane containing x prime OX and y prime OY is said to be an invariant during this reflection. Why? Since the straight line D is itself in the plane containing the axis x prime OX and y prime OY. Now let's learn about another mapping, which is the rotation. As you see here, we have the points I, the vector IE and the vector IF. If we rotate one of these vectors by an angle alpha, as you see here, we are rotating the vector IF by an angle alpha. This is said to be the rotation around the center I by an angle alpha. So we call it RI alpha. What about the inverse of this rotation? Well, there is something which is very important. The positive orientation is anti-clockwise. So when we talked about the rotation, it was by an angle alpha anti-clockwise. While here, if we talk about its inverse, if you know something, the vector will move clockwise. Here we talk about the negative orientation by minus alpha. Well, as you see here, the inverse of the rotation I minus 1 around I by an angle alpha is equal to the rotation around the center I by an angle minus alpha. Rotation is one of the most important transformation mappings that can be applied in planes. Thank you for watching. If you enjoyed this video, please like, share and subscribe.